Hello, this is Dr. Lennon. We're going to go over the final exam review. Again, this is a lot of the questions from Test 1 and Test 2. This first one is computing some Riemann sums. Again, we're just basically approximating the area using a bunch of rectangles. So the first thing is to figure out the width of each rectangle, which we use the formula b minus a over n, where n is the number of rectangles. So we're going from 12 to 8, or from 8 to 12 rather, so 12 minus 8 over 5 comes out to 0.8. So that's the width of each rectangle. So for A, when we're doing the... so then also we want to figure out what our partition is. So basically we start at the low number 8, and then we add 0.8 each time until we get to 12, and then that is our partition. So for the for part A, for the left rectangles, we use the first 5 numbers, whereas for the second part, part B, we use the last 5 numbers. So those are the things that we plug into our function, y equals the natural log of x, to get the height of each rectangle respectively. So for A, the area is going to be given by approximately 0.8 times the natural log of 8 plus the natural log of 8.8 plus the natural log of 9.6 plus the natural log of 10.4 plus the natural log of 11.2. And we can approximate that in our calculator. So let me do that quickly, and I'll just round that answer to 2 decimal places. So that comes out to about 9.02. So then B is going to be no different, except for we are going to be starting not at 8, but at 8.8, and instead of finishing at 11.2, we'll finish at 12. So we get 0.8 times natural log of 8.8 plus natural log of 9.6 plus natural log of 10.4 plus the natural log of 11.2 plus the natural log of 12, and that's it. So let's figure out what that comes out to. So that comes out to about 9.34. So a good estimate for the average, if we had to use one, is probably a average of those two values, but here they just explicitly ask for the left and right approximation, so those are the 2 respective answers. So let's move on to part 2. So for number 2, we're just evaluating some integrals using the picture. So again, the integrals are representing signed areas. So basically, if the area is above the x-axis and we're moving from left to right, it's going to be positive, and below it's going to be negative. So for the first one, we're going from 0 to 5, so we're moving in the left to right direction. So basically, the top area 7 is positive, and the bottom area is minus 6, so that comes out to 1. For B, if you're looking at the absolute value, it would turn all the y values into positive y values. So essentially, the second hump would get flipped over the x-axis, and we'd end up with 7 plus 6, which would come out to 13. And then the last one, we're traversing, but in the opposite direction. So for part A, we're going this way. B, for part C, we're going from right to left. So we're taking the reverse orientation, which basically is going to change the sign. So we'd have -7 and then +6. So this would come out to -1. And that's basically it. So we're just checking to understand that you understand that above the x-axis is positive, below is negative if we're going left to right, and everything switches right to left. So let's move on to number 3. So 5 is just a U-substitution, so finding a general antiderivative. So we want to let u be x squared minus 5, and then find du. So du will be 2x dx. So then the easiest way I recommend is just solving for dx. So du divided by 2x is equal to dx. And then we can substitute out. So basically, this integral changes to the integral. The x is still there. X squared minus 4 becomes u, so we have u to the 5th power. And then we can replace dx by du divided by 2x. And then our x's will cancel off. So we'll just have the integral of u to the 5th du, which can be done with one of the basic shortcuts. So this just becomes u to the 6th over 6 plus a general constant of integration. And if we want to switch back to the original variables, u can be replaced by x squared minus, I wrote 5 for some reason. When I originally substituted, that should be 4. But it changes back to x squared minus 4 in parentheses. And that is it. So for 4, we're integrating again, finding a general antiderivative. But now we have a product of two different types of functions. 4x is a polynomial and e to the 2x is an exponential. So we've done a few of these. In this case, remember, typically what it's easier to do is let u be the polynomial. So u is going to be 4x, and dv is going to be our e to the 2x. So then we find du, which is just 4, and v, which is e to the 2x divided by 2. So our integral will become uv minus the integral of v du. So we get 4x times e to the 2x over 2 minus the integral of v, so e to the 2x over 2 times 4 dx. And once we finish this up, this is our general antiderivative. So we end up with 4x over 2 is 2x, so we get 2x e to the 2x minus, again, 4 over 2 is 2, so we're just integrating 2 e to the 2x. And the general antiderivative rule for an exponential and continuous form is just going to be e to the 2x over 2 here. So this simplifies to 2x e to the 2x minus e to the 2x. So when you divide by the 2, it cancels with the 2 in front, then just plus a constant of integration. And that's it. So for 5, we want to find the area between the two curves. So again, the picture here, basically we're looking for the difference between the two curves from x equals 0 to 1. So in this case, the parabola part is lower, so you've got some kind of like parabola here. Then you've got a line somewhere up here. So basically we've got, we're going from 0 to 1, so we've got some, so this cuts through here, maybe something like that. So we're looking for the area of some shaded region like this. So the area here is the 0 to 1 are the limits, and then we just want to subtract the function. So we have 2x plus 5 minus x squared plus 1 dx. So our integral is just from 0 to 1, and we end up with minus x squared plus 2x, and then positive 5 minus 1 is plus 4. So we just want to find the antiderivative. So we end up with minus x cubed over 3 plus x squared plus 4x. And we're going from 0 to 1. Again, we're just doing a polynomial here. So when you plug in 0, everything vanishes. So really that's all we have to do is plug in the 1. So we get minus 1 cubed over 3 plus 1 squared plus 4 times 1. And this will come out to 5 minus a third, which 5 minus a third, so that's just going to come out to 14/3. And that is your answer for this one. So really, if you get the setup right, the integration's a piece of cake. So for 6, we have a separable differential equation. So remember what we want to do. First, multiply so that we have dy on one side and dx on the other. So we have xy dy equals y squared plus 1 dx. And then basically we want to move all the y's to the left and all the x's to the right via multiplication and division. So the best way to do that is divide by x on this side, and so we're going to have to do it on the other side. So that'll move the x's right, and then the y squared plus 1 needs to move to the other side. So we also want to divide by y squared plus 1 on both sides. So we'll end up with y over y squared plus 1 dy on the left, and just 1 over x dx on the right. So that means that we can integrate, now that we only have y's on the left and x's on the right, we have separated the variables, so to speak. So the right-hand side is just going to be the natural log of the absolute value of x. We can add the constant of integration if we want there. And then the integral of y over y squared plus 1 is a u-substitution. So the u-substitution on the left, we can do that over here. Basically, we end up with u is the denominator, y squared plus 1. So du is going to be 2y dy. So divide by 2y. We end up with our du over 2y is equal to dy. So then we can change our integral. So our integral on the left is going to be the integral of y over u times du over 2y. So this is how our y's drop out. And then we just have the antiderivative of basically 1/2 times 1 over u du. So this is just going to be 1/2 natural log of the absolute value of u. We've already got the constant on the right-hand side, so I'm not writing plus a constant. So anyway, this comes out to 1/2 natural log of the absolute value. I'm going to change u back to y squared plus 1. Technically, we don't even need an absolute value there because y squared plus 1 is always going to be positive. So sometimes they'll require us to solve for y. Typically, I don't do that on my test because, you know, it's a family of curves. But let's suppose we wanted to. Basically, we want to isolate y. So if we wanted to do that, we could multiply by 2, and we'd end up with the natural log of absolute value of y squared plus 1 is equal to 2 natural log absolute value of x plus 2c. Then to undo natural log, we would make both sides the exponent of e. So we would have y squared plus 1 is equal to e to the 2 natural log absolute value of x plus 2c. Okay, so y squared plus 1 would equal e to the 2 natural log. Actually, why don't we use a little trick here? We can put that 2 back inside the exponent, so it's really just the natural log of x squared plus 2c. So we can rewrite this as y squared plus 1 is equal to e to the natural log of x squared times e to the 2c. Okay, so then we have y squared plus 1. E to the natural log of x squared will cancel, so we'll have x squared times e to the 2c, which is really just an arbitrary constant. So we can actually solve for y squared now by subtracting 1 and then taking the square root. So we can say, okay, y is equal to x squared times e to the 2c minus 1, and then we would need the square root of all that business. And then a common trick is, since e to the 2c is a arbitrary constant, we could just call that by a new arbitrary constant name, say capital K, x squared minus 1, something like that. And that would be the solution for y. Again, that's not typically necessary for us, so usually I would just end the problem once we've found the solution up here. So usually I stop there. But okay, if you want to solve for y, you can, but usually that requires just a bunch of algebraic manipulation. Okay, so on this problem, I actually ask you to tell me why it converges first, so we can just say that briefly. Basically, if you have the integral from, basically this converges, so you may want to look this up, but we called it the p-series test. So if you have 1 over x to the p and you're integrating from some constant to infinity, some positive constant to infinity, it converges if p is greater than 0 and diverges if p is less than or equal to 0. So we say this converges by p-series test with p equal to 3 over 2, which is greater than 1. So you may want to refer back to that in the notes. Okay, so now we want to find out what it actually converges to. So we want to basically do the integral by replacing infinity with a limit as t goes to infinity. So this is going to be the limit as t goes to infinity of the integral of 4 to t of, and again, usually it's useful to rewrite this as x to a negative exponent. Okay, that just makes taking the antiderivative easier. So this is going to be the limit as t goes to infinity of, again, add 1 to the power and then divide by that. So we're going to get negative 2 x to the minus 1/2 from 4 to infinity. If you add 1 to negative 3 over 2, you get the power of negative 1/2, and then 1 divided by negative 1/2 is actually just negative 2. So now we can basically plug both of these things in. Maybe I'll write one additional step because it might be easier to see if we think about this as negative 2 divided by the square root of x. I meant the top limit. I wrote infinity, but we should be writing t because we're taking the limit. So this ends up as the limit as t goes to infinity of negative 2 over the square root of t minus negative 2 over the square root of 4. We know the limit of the first term as t goes to infinity, the denominator is going to infinity, which makes the first term go to 0. So basically this becomes 0 plus 1, so the integral just converges to 1. And that is it. So for 8 here, we want to evaluate and then find the domain. So this is a three-dimensional function, 2 input variables, 1 output variable. So f of 1, 5, we're just replacing y by 5 and x by 1, and it's going to give us a z value. So we end up with the square root of 4, which is just equal to 2. So pretty easy. So for b, what we want to do is we want to find all ordered pairs that make the output exist. So basically the ordered pair, since these are real valued functions, is going to exist as long as y minus x is greater than or equal to 0. So that's the same as y being greater than or equal to x, right? We need the operand of the square root of y minus x to be non-negative. If it's negative, then you'd end up with a complex value, and we're only considering real values here. So the sketch of the domain is just the ordered pairs that satisfy this inequality on the xy plane. So all the places where y is equal to x are just on the 45-degree angle line y equals x, and then the places where y is greater than x are shaded above. So this is the domain. And that's it. So again, it's pretty much the same as domains with 2 variable functions. Usually what we're doing is we're making sure what's beneath a radical is non-negative, or that we're not dividing by 0 somewhere, and then we just want to sketch the picture. And since the domain is based on 2 variables here, the picture can be represented as some subsection of the xy plane. All right, so let's move on to the last one. Okay, so for this one, we just want to find the first partial derivatives. Again, when we're taking the partial derivative with respect to x, we just want to treat y as a constant and take the derivative of the things that are involving x. So the first term, x squared y to the 4th, you just treat y as a constant, and you ask yourself, well, what's the derivative of x squared? Well, that would be 2x. So we would have derivative 2x y to the 4th. And then when we're taking the derivative of the second term, minus 2xy to the 5th, what's the derivative of minus 2x? It would be just minus 2. So this becomes minus 2y to the 5th. And then the y partial derivative, same thing, but now we think of y as the variable and x as the constant. So what's the derivative of y to the 4th? 4y cubed. So we'd end up with 4x squared y cubed. And for the second term, the derivative of 5y to the y to the 5th would be 5y to the 4th. Multiply the 5 with the negative 2, we get minus 10x y to the 4th. And those are your 2 partial derivatives. So for number 10, on the review, I had something where we were trying to find a saddle point using a second derivative test for multivariable functions, but we didn't get there. So probably what's going to happen is I'm just going to have another find the partial derivative, and probably it will involve a chain rule in some capacity, something like that. So, we could do a sample one here. So let's say find the first partial derivatives. Of, let's say, f of xy is equal to, let's say, of 8x plus 5y to the 7th. So the x partial derivative, for both of them, basically what we're going to have to do is set up a chain rule. So our inside function is 8x plus 5y, and our outside function is just going to be t to the 7th. So the derivative of the outside is just going to be 7t to the 6th, because t is just a placeholder variable. But the derivative of the inside, we need to take the derivative of 8x plus 5y using the x partial derivative. So the derivative of 8x would just be 8, and the derivative of 5y would be 0, since we're treating y as a constant. So now that we have that, we can actually find this partial derivative because we multiply in prime by out prime. So we do 8 times 7, and then we change t back to 8x plus 5y. So 8x plus 5y to the 6th. So we end up with our answer 56 times 8x plus 5y to the 6th. And that's that. For the y partial, basically it's the exact same setup, but the partial derivatives are just going to change a little bit. So when we're doing the y partial derivative, what happens is our inside is still 8x plus 5y, and our outside is t to the 7th. However, the derivative of the inside, now we're taking the y partial. So this becomes 5, and the derivative of the outside is still 7t to the 6th. So rather than multiplying by 8, now we're multiplying by 5. So we end up with 5 times 7, then change t back to 8x plus 5y. And then this is raised to the 6th power. So your y partial derivative is just going to be 35, 8x plus 5y to the 6th. And that is it. So good luck on the final. And this is Dr. Lennon signing off.